Hello students, in the last class we completed the nomenclature of complexes at where only one metal atom is there, simple naming of the complexes. I dealt already the different types of rules and I given some examples. But in some cases the particular complex compounds carry more than one metal and these particular metal atoms are bridged by the ligands. Such complex what we call bridged complexes. Let us see how to name these bridged complex compounds. Bridged complex compounds. Look here the bridged complex compounds. Now I write a complex . Let me write amines. RSC taken 4 times. RSC taken 4 times. Let me say it is Cl4. Cl4. How to know this particular complex carrying 2 metal atoms bridged by hydroxy groups? Now, to show the bridging for this particular bridged complex, we use a prefix mu. Look here, the mu stands for bridging. Now you see next, how many bridges are there? 2. Say first di. Di, 2 are bridging. To show the bridging, to indicate the bridging, we are writing mu. Di mu, 2 are bridging. Di mu. What are bridging? Hydroxo. Di mu, hydroxo. Di mu, hydroxo. Next, we have to represent this particular on either side. Therefore, we are writing bis. Bis. Di, 2 bridges. Mu stands for bridging. Hydroxo, bridging. Next, bis. Bis stands for 2 times or giving the meaning of on either side. On either side or 2 times. Bis. Put a big bracket. Then, what are on either side? Tetramine. 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 Followed by next cobalt, tetramine, cobalt on either side. And we have to check it again. What is the oxidation number? Now 4 chlorions, 2 OH. And again total how many charges? 6 charges. These 6 charges are shared by 2 cobalt atoms. 2 cobalt atoms. Then each cobalt is becoming what? Plus 3. Followed 4 plus 2, 6. 6 charges you have to share by 2. Then the cobalt oxidation number becoming what? 3. Cobalt 3. Close the bracket. Whatever the anion is there, put at the end. This is what? Chloride. This is chloride. This is the way how we name this particular bridged complex compound. So what I said, first see the number of bridges. Di. To represent the bridge, we are using prefix mu. Then what are bridging? Hydroxo. To represent on either side, say bis we are writing. Bis stands for either twice you take or on either side. Then after base, a big bracket, tetramine, cobalt and oxidation number 4 plus 2, 6 shared by 2 cobalt atoms. Therefore, cobalt 3 chloride. This is the way we name this particular bridged complexes. Let me write one more easy complex. I'll write. Look the board. Iron carbonyl I am writing now, FeCO, then it is what? CO, or let me say instead of writing bridges, we can also write this particular CO taken thrice, then CO taken thrice, and again we can write on either side. So according to what I said here, first you have to show the number of bridges. How many bridges are there? 3. Let me write first tri, 3 bridges. Tri. What are bridging? Carbonyl. Then to represent the bridges, what I said? Mu. Tri mu. 3 bridges. What are bridging? Carbonyl. Take it is carbonyl. Carbonyl. Tri mu. 3 bridges. Carbonyl are bridging. Next, to represent on either side, what I said? Put B and big bracket you write. Then whatever there on other side on either side can represent this particular tricarbonyl. Trimu carbonyl base, tricarbonyl, iron. Iron oxidation number is 0. Why? All are carbonyl ligands. You know well. Carbonyl is what? Neutral ligand. Therefore, there is no charge in the complex. Therefore, iron is becoming what? Oxidation number 0. This is the way to name this particular complex. Trimu carbonyl base, tricarbonyl, iron 0 is the name of this particular complex. So, in this way, we name this particular bridge complex compounds. And one more classification is there. In some cases, the complex compounds are carrying two coordination pairs, or one is representing the cation, the other representing the anion. So, the complex is containing complex cation and anion. How to name those particular complexes? In some, there is two coordination pairs are there, neighboring coordination pairs. How to name those particular complexes? Let me show. Next, we see the complexes containing complex cation and anion. Complexes containing complex cation and anion. Complex cation and anion means what? In some of the complex there will be neighboring two coordination pairs. One represents cation, the other represents anion. Now I am giving a simple complex in this. CO, NS taken 6, hexamine, and again Cr, Cl taken 6. Consider complex cation, complex anion. The first coordinate pair is cation and second coordinate pair is anion. Next, how to name this particular complex? Easy, half and half you have to name. You have to divide into half and half. Then first cation followed by anion, you have to name it. Once I am saying it is what? Cation, it is anion. Cobalt, you have to normally say the name of the cobalt as cobalt only, but this represents what? Anion. Therefore, you have to use a suffix 8. Therefore, you have to say this one is a chromate. This normally you have to call it what? Cobalt. So, you have to see next oxidation number. According to the coordination number, first you decide the oxidation number. Coordination number is 6. Generally, cobalt oxidation number is what? +3. Here also you see chromium, coordination number is 6. Therefore, chromium also becomes oxidation number +3. Both are having +3 oxidation number. Naming is simple. See, hexamine cobalt 3 first half, hexamine cobalt 3 in a single line you have to write hexachloro chromate 3, hexachlorochromate 3, hexamine cobalt 3, hexachlorochromate 3. Since it is cation, there is no change in the name of the metal. It is actually representing anion. Therefore, I made it what? 8 chromate 3. Let me write one more. Now you are taking a platinum tetramine, you write NS taken 4 platinum tetramine. Then let me say PT Cl6, you take Cl6. Now this is representing cation, this is representing what? Anion. Then name it tetramine platinum 2. Why I am taking platinum 2? One's coordination number is 4. The metal oxidation number is what? +2. The platinum is actually +2. Here the same thing, platinum. What is the coordination number? 6. Platinum already given. Wherever the platinum coordination number is 6, that will be oxidation number. That will be having the oxidation number +4. This is cation. This is the anion. This you have to normally name platinum as platinum only. But the second half is actually representing it is anionic. Therefore, platinate you have to say. So, tetramine platinum 2. Why I am writing 2? Coordination number 4. Oxidation number of platinum is what? +2. Therefore, platinum 2. Second half is actually having coordination number 6. Therefore, again hexachloroplatinate. Hexachloroplatinate 4. Hexachloroplatinate 4. So, it is tetramine platinum 2, hexachloroplatinate 4. This is what the naming of the complexes where two coordination spheres are there. One is representing cation, other representing anion. So this is what different types of nomenclature. In some of the complexes, only one metal atom is there, simple naming. As shown in some of the complexes, two metal atoms bridged by a ligand, those are bridged complexes. Next, just now I shown some of the complex carrying complex cation and anion are two coordination spheres. Now, then a complex formula is given, somewhat you can easily name it. Once a name of the complex is given, it is a little bit difficult to write the chemical formula of a complex. Now I will write some of the names of the complexes, then how to frame the formula of a complex, let us see. So once name is given, how to frame the formula of a complex, I will make it easy how to write this particular. Once name is given, how to frame the formula of a complex. Write the chemical formulae for the following complexes. Write the chemical formulae for the following names of the complexes. Write the chemical formulae for the following names of the complexes. Writing the C now. Base ethylene diamine, base ethylene diamine, cobalt 3 ion, base ethylene diamine, cobalt 3 ion, tetracyanone, nickelate 0, nickelate 0 ion, tetracyanone, nickelate 0 ion. Next, tetramine dichloro platinum 4 chloride, tetramine dichloro platinum 4 chloride. Let me write one more. Tris ethylene diamine, cobalt 3 chloride, Like this, in the examination they may give the formula. Instead of giving the formula of a complex, they will give the name of the complex. How to frame the chemical formula for a given name of the complex. While writing these particular names of complexes, you have to follow that. First metal ion you have to write. What do you have to write? First metal ion you have to write. Then take the negative ligands again in the alphabetical order. First metal ion, next followed by negative ligands only you have to put in the alphabetical order. After negative ligands, neutral and positive ligands you have to write. Here this particular guidelines you have to follow. First metal ion, followed by negative ligands in the alphabetical order. Then again neutral and positive ligands you have to write. Now, base ethylene diamine, cobalt 3 ion. First what I said, you have to write the metal. Yes, metal, cobalt I written. Then base ethylene diamine, cobalt 3 ion, base ethylene diamine, cobalt 3 ion, En taken twice, base ethylene diamine, cobalt 3 ion, then you can take it what plus 3. This is not looking very correct. Once you talk about this particular coordination number 4 and cobalt is actually not plus 3, there should be a little correction should be there. Bisethylene diamine, oxalato, cobalt 3. Base ethylenediamine oxalato cobalt 3 ion. Base ethylenediamine oxalato cobalt 3 ion. Now, first we have to write the metal. Yes, metal cobalt. Then what I said, after the metal you have to write the negative ligand. Write oxalato. Look here, C2O4 oxalato. Then base ethylenediamine 2 times you write, 2 times. Now base ethylenediamine oxalato cobalt plus 3 how to make. How many negative charges are there inside? 2. Oxalato negative charges are 2. Therefore cobalt is becoming plus 2 only. Then you have to make it actually cobalt plus 3. Therefore a plus charge is required. Therefore it is base ethylenediamine oxalato cobalt 3 ion. Why we are putting this particular positive charge? It is not 8, therefore it is not representing anionic complex. It is what? Cationic. Therefore CO C2O4 En taken twice, the first complex. Coming to the next one, tetracyano nickelate 0. First you write nickel, first metal, only one type of ligands are there. Then you write tetracyano. Then nickelate 0. Nickelate stands for it is carrying what? Negative charge, the anionic complex. Moreover, you have to make the oxidation number of nickel 0. Then 4 charges you have to put. Then it is tetracyano nickelate 0 ion. Coming to the next one, tetramine dichloro platinum 4 chloride. Now tetramine, first write platinum. Yes, platinum. Then dichloro, write Cl2. After the metal you have to write the negative ligands. Then tetramine NS3 taken 4 times. Then chloride is said, and moreover oxidation number is what? 4. Only 2 chlorides are there to make platinum plus 4 oxidation number. 2 more chlorides are required. Therefore it is tetramine dichloro platinum 4 chloride. Coming to the next one, trace ethylenediamine cobalt 3 chloride. Trace ethylenediamine, first you write cobalt, trace ethylenediamine, yes, trace ethylenediamine, cobalt 3 chloride is said, then cobalt should be plus 3 and 3 chloride outside. Like this, whenever the name of the complex is given, first you write metal, next negative ligands, follow the alphabetical order. If more than one negative ligands are there, then followed by neutral and positive ligand. This is the way to write the formula of a complex when name of a complex is given. Right. See, in the complex compound, first we are completed the ligands, coordination number, oxidation number, theories of complex compounds, Werner theory, Sidgwick's theory. Then we entered into nomenclature. This is all we are completed. Now let us see the next theory, valence bond theory. Valence bond theory. Valence bond theory, VBT. Let me explain what are the important postulates of this particular valence bond theory. Postulates. Valence bond theory. In metal complexes, the vacant sp, d and f orbitals, s, p, d and f orbital. The vacant sp, d and f orbitals hybridize together, produce hybrid orbitals, equal to its coordination number. The SPD and F vacant SPD and F orbitals undergoing hybridization, producing hybrid orbitals equal to its coordination number. These hybrid orbitals of metal overlapping with ligand orbitals forming the covalent bonds or chemical bonds. The vacant sp,d and f orbitals of metal ion hybridize together produce hybrid orbitals equal to its coordination number. These hybrid orbitals overlapping the ligand orbitals form covalent bonds or chemical bonds. Now, based on the coordination number, based on the coordination number and hybridization. Based on the coordination number and hybridization, we can decide the geometry. Based on the coordination number and hybridization, we can decide the geometry. The table is there, and what is the coordination number, hybridization, what is the geometry? A small table is there. Let us make the same table now. Consider coordination number 2, well known to you. Then it is what? SP, hybridization, SP. The geometry is coming to be linear geometry. The geometry linear. See, coordination number 2, SP, hybridization, and geometry coming to be linear. Consider the coordination number 3, and you know well, this is what SP2 hybridization, and the geometry is what trigonal planar geometry, trigonal planar. Next to take coordination number 4, then it is possible hybridization is what? SP3. SP3, it is tetrahedral geometry, tetrahedral. Coordination number 4, SP3, it is what? Tetrahedral geometry. Another choice is also there. Whenever coordinate number is 4, another possible geometry you can say square planar. Another possibility I am writing, see, for DSP2 hybridization, then you can take it is square planar geometry. Coordinate number 4, 2 possibilities are there. One set is involving SP3, that will be tetrahedral. One set is involving DSP2 hybridization, the geometry coming to be square planar. But many times I have seen the question in a different entrance exams, wherever DSP2 hybridization we are saying, out of 5 d orbitals, what actually the d orbital is involving? Yes, you know in the d subshell 5 d orbitals are there, dxy, dxz, dyz, d square minus y square, and dz square. Out of 5 d orbitals, which d orbital is actually participating in DSP2 hybridization? That is very important. I have seen many times this particular question in the different entrance exams. The d orbital participating in DSP2 is, that is what d n minus 1d shows that inner d orbital. What d orbital it is? D x square minus y square orbital, only involving in DSP2 hybridization. This is very important to remember. Next, coordination number 5, that is containing the same table, coordination number 5. Once you take the coordination number 5, then the possible hybridization is D sp3, or you can take sp3d. sp3 stands for inner orbital complex, and sp3d stands for outer orbital complex. And again, out of 5 d orbitals, again here what is the d orbital participating in this particular hybridization also? In this particular hybridization, either it may be inner n minus 1d, this will be dz square, or outer nd, this will be dz square. This particular dz square orbitals involving in this, either you take dsp3 or sp3d, the d orbital participating in hybridization is what? Dz square. Come on, say about the possible geometry, it is what? Trigonal bipyramid geometry. Coming to the next one, coordinate number 6 you take. Then you know well, there is actually 2 possibilities of hybridizations. One is inner, one is outer. Then it is again D2sp3 hybridization, or you can consider sp3d2. Once you are writing D2sp3, this will be inner orbital complex, and sp3d2, that will be outer orbital complex. Whatever it may be, inner or outer, 2 d orbitals are participating here. What are the 2 d orbitals participating in this particular hybridization? Now it will be n minus 1d, inner I am writing, the EG set of orbitals, EG set means what? dx square minus y square, dz square, these 2 orbitals are participating in this particular hybridization. N minus 1d, it will be dx square minus y square and dz square, these are the orbitals participating. Once you talk about outer orbital complex or sp3d2 outer orbital hybridization, see It is what d2 inner d orbitals, sp3 d2 outer d orbital. Outer d orbital we represent like this, nd. This will be d square minus y square and d z square. D square minus y square and d z square. Whatever it may be, inner or outer, the geometry of the complex is what? Octahedral geometry. Like this, based on coordination number, hybridization, we can decide the geometry of a complex according to valence bond theory. Next postulate, let me discuss what is the next postulate under valence bond theory. Next one, third. In the hybridization, once inner orbitals are involving, say n minus 1d. In the hybridization, if inner orbitals are involving, we represent that by n minus 1d. Imagine in 3D series, 3D orbitals involving. 3D series, 3D orbitals are involving. Say inner orbitals are involving, 3D is involving. The resulting hybrid orbital is found to be d2 sp3, d2 sp3, d2 sp3. Then once inner orbitals involving, 3D is involving, the hybrid orbital produced is d2 sp3. Then that particular complex we call inner orbital complex. The complex is inner orbital complex, you see, or you say low spin complex, or you can also call spin paid complex. Then this will be definitely diamagnetic complex. Why diamagnetic? Electrons are getting paid, then you are getting inner orbital complex, then d2 sp3, inner orbital complex, low spin, spin paid, and that particular complex, once electrons are getting paid, there is no unpaid electron left over, therefore the resulting complex is what? Diamagnetic. The same thing we can show by a box diagram or valence bond diagram. Valence bond diagram, you see the box diagram, either the way we can represent this particular hybridization. Now you see it is actually 3D orbitals, 3D, 4s, and you consider 4p. 3D, 4s and 4p you take. What is said? d2 sp3, 2d orbitals from d, 1, 2, 3, 4, 5, 6 you consider. Then d2 sp3 I said, this is the hybridization, we consider d2 sp3 hybrid orbital. This represents inner orbital complex, low spin, spin paid, diamagnetic. Next, the same point. Now, if outer orbitals are involving, say nd, nd means let us consider 4d. In 3D series, if 4d is involving, in 3D series of element, 4d orbital is involving. That means what? That is outer orbital is involving. Then the hybrid orbitals produced will be, consider sp3d2. The complex is, you can say, outer orbital complex, or you say high spin complex, or you say spin free complex. Definitely there is no pairing of electrons. The complex is what? Paramagnetic. What you are saying now? Outer orbital complex, sp3d2 hybridization, outer orbital complex, high spin complex, spin free complex, and once the electrons are not getting paid, remaining unpaid electrons there, unpaid electrons are remaining in the complex, that particular complex exhibiting paramagnetic property, therefore it is paramagnetic. The same diagram, how to represent in this particular outer orbital? I am writing below 4s, I am writing one more 4s orbital, below 4p to represent, to make you to easily understand this particular, then 4s, this is actually 4p. Then I am writing outer orbital 4d, I am writing after this, consider it is what? 4d. 6 orbitals are required, 1, 2, 3, 4, 5, 6. Then you see what is this particular hybridization? This will be sp3 d2 hybridization. This is d2 sp3, this is sp3 d2, inner, outer, and low spin, spin paid, high spin, spin free, it is diamagnetic, it is paramagnetic. According to this type of hybridization, we can decide whether a complex is inner orbital complex or outer orbital complex. Next, last postulate what we can say, according to this particular theory, a ligand molecule should carry at least one lone pair of electron for bonding. According to this particular theory, a ligand molecule should carry at least one lone pair of electron for bonding. These are the some important, it is valence bond theory, important postulates of this valence bond theory. Next, what are the demerits of this particular theory, defects of this particular theory? Let us discuss defects of valence bond theory. Defects in valence bond theory, defects. Defects under valence bond theory. First one. This theory is completely based on magnetic properties, remember. This theory is completely based on magnetic properties. This theory is actually proposed by Linus Pauling, and he has prepared different complexes, and those complexes are taken into a Guy balance, a magnetic balance. When that particular balance is showing the diamagnetic nature, he said inner orbital. If that is showing the paramagnetic nature, he said that is what outer orbital complex. This particular, based on the magnetic property only, he had decided which is outer orbital complex, which is inner orbital complex. Diamagnetic inner, paramagnetic outer. So this theory is completely based on magnetic properties of the complexes. First one. Next, more stress on metal cation. More stress on metal cation. More stress on metal cation, nature of the ligands is completely neglected. More stress on metal cation is concentrated more on the metal cation, but nature of the ligands completely neglected. Nature of the ligands. Nature of the ligands completely neglected. More stress on metal cation, it concentrated much more on the metal cation, but the nature of the ligands is completely neglected. This particular inner orbital and outer orbital complex you are getting, that is much more dependent on nature of the ligand. But when he has proposed this particular theory, he doesn't know much about the ligands. Yes, some of the ligands are actually weak field ligands, some of the ligands are actually strong field ligands. But at that time, you don't know actually which is weak field, which is strong field. Therefore, not considered the nature and the properties of ligands, only based on the magnetic properties, he has decided which is inner and which is outer. Next, he has simply given the explanation inner orbital complex and outer orbital complex. He simply explained one is inner, one is outer. But why you are getting an inner orbital complex, why you are getting an outer orbital complex, he has not given any clear explanation. There is no suitable explanation for the formation of inner orbital and outer orbital complexes, especially in valence bond theory. In valence bond theory, there is no suitable explanation for the formation of inner and outer orbital complexes. Next, this theory also fails to explain the correct geometries of some of the metal complexes. CuNS3 taken 4 times, plus 2 complex to take plus 2. 4 coordinates number is there. Then copper is actually D9 in this. What actually copper electronic configuration D10S1 plus 2 electronic config plus 2 oxidation number, it is becoming what D9. D9 d orbitals are fully filled, it should be sp3 and tetrahedral. According to valence bond theory, it should be sp3 and tetrahedral. But remember, experimental results are showing it is square planar. It is square planar. It is square planar. It is square planar. The hybridization is also little bit abnormal. It is sp to d hybridization. So this particular complex, according to valence bond theory, we can say as what sp3 and tetrahedral. But experimental results are giving information it is square planar with hybridization sp to d. Hybridization sp to d. In this way, these are actually some of the defects under valence bond theory. So valence bond theory, the postulates of valence bond theory, some of the defects under valence bond theory. Next, advanced theory by which we can actually overcome some of the defects of valence bond theory, that is crystal field theory. Next, we go into details of detailed discussion about that crystal field theory. Next, let us see crystal field theory. Crystal field. It's what CFT, crystal field theory. This particular theory we can also call it as electrostatic theory. Electrostatic theory. Crystal field theory, or you can call it as what electrostatic theory. Let us see what are the important postulates under crystal field theory. 1. See, in metal complexes, metal to ligand bond is purely electrostatic force. It is highly ionic, 100% ionic it says. In metal complexes, metal to ligand bond is purely electrostatic force, highly ionic. There is no overlapping of orbitals between the metal and the ligand, and there is no transfer of electrons between the metal and the ligand. What it says is there is no overlapping of orbitals between the metal and the ligand. There is no transfer of electrons between the metal and the ligand. Yes, no transfer of electrons. Metal to ligand bond is purely electrostatic force and it is highly ionic. There is no overlapping of orbitals and no transfer of electrons between the metal and the ligand. This is the first postulate of crystal field theory. Next, second. Metal ions are occupied by different types of ligands. Consider it may be negative ligand or positive or neutral ligand. Metal ions are occupied by different types of ligands, but there may be a negative ligand or the neutral ligand or the positive ligand. According to this particular theory, negative ligand is considered what a point charge. Negative ligand we have to consider what a point charge. Negative ligand is what a point charge. Take any negative ligand like chloro ligand, cyano ligand, and bromo ligand, nitro ligand. All the negative ligands we can consider these as what a point charge. Next, suppose you are considering a neutral ligand. Neutral ligand is considered what a dipole. Neutral ligand we can consider what a dipole. You take negative ligands like either it may be Cl minus or Cn minus, or you take NO2 minus. What I said, point charges. Now you are taking a aqua ligand like this particular H2O. Aqua ligand like this particular H2O. You can take it as what a dipole. This is as what a dipole. Next. Under the influence of different field strengths of the ligands, different field strengths of the ligands. Some of the ligands are weak field ligands, some of the ligands are strong field ligands, and based on this particular field strengths of the ligands, under the influence of different field strengths of the ligand, the 5d orbitals splitting into different energy levels. 5d orbitals splitting into different energy levels. Like this, 5d orbitals, we can take as dxy, dxz, dyz, dx square minus y square, dz square. These are the 5d orbitals. These 5d orbitals under the influence of a ligand like it. Maybe you take cyano ligand or chloro ligand, any ligand. Under the influence of this different field strengths of the ligand, the 5d orbitals splitting into different energy levels. What to say? These are what higher energy level, you can consider what easy set of orbital, and lower energy level T to G set of orbitals, T to G and easy. The energy difference between these two orbitals coming to be what delta O. See, delta stands for energy difference, O stands for octahedral geometry. Like this, the 5d orbitals under the influence of different field strengths splitting into different energy levels. Lower energy level T to Z, higher energy level EZ. In EZ, the orbitals are, it is dx square minus y square and dz square, and these are three. Consider dxy, dxz, dyz. These are the orbitals lower energy level and higher energy levels. Next, according to this particular crystal field theory, we can thoroughly explain the color properties, the various color properties of different complexes. According to crystal field theory, we can thoroughly explain the color properties, the various color properties of different complexes due to d orbital to d orbital electronic transitions. D orbital to d orbital electronic transition. What is this d orbital to d orbital? Consider 5 d orbitals. A d3 electronic configuration will take 1, 2, 3. Let me write d3 electronic configuration. This particular d orbital splitting into different energy levels. Yes, after the splitting, electronic arrangement is like this. Electronic arrangement is like this. Consider it is what easy I said. This is T2Z, T2Z and easy. This one will be then what do you say delta O. After splitting of these particular d orbitals, the 3 electrons entering into lower energy levels. Look here, lower energy levels. The energy difference between the lower energy level T2Z and higher level EZ is very less. It is more or less equal to visible region of light. What I am saying, after the splitting, the energy difference between lower end level and higher end level is what less. It is more or less equal to visible region of light. Visible region of light. For the electronic transition, this absorbing energy from this particular visible region, imagine X color is absorbed. X color is absorbed, the electron is what excited. The electron is actually excited to higher energy level like this. Take higher energy level. Electron the higher energy level is less stable. Again, it is de-excited back to the ground state. While excitation absorption of energy, while de-excitation, yes, the absorbed energy is what transmitted. Whatever the color it is transmitting, imagine it is actually transmitting a Y color, then that will be the color of the complex. This particular 2 are d orbitals only. Lower energy level, higher energy level, both are d orbitals only. Therefore, what we call this is d orbital to d orbital electronic transition. Specifically, we are also saying T2Z to EZ electronic transitions. Based on this particular electronic transitions, T2Z to EZ or D2D electronic transitions, we can thoroughly explain the color properties according to crystal field theory. One more possibility there, then according to this particular crystal field theory, we can thoroughly explain the various magnetic properties. How we explain the magnetic properties? See. The various magnetic properties we can also explain based on splitting of d orbitals under the influence of different field strengths of the ligand. Splitting of d orbitals under the influence of different field strengths of the ligands. Look here. Now you consider the weak field ligand and the strong field ligand. I am writing a d orbital. I am writing d orbitals or electronic configuration with 6 electrons. Let me write 1, 2, 3, 4, 5, 6 electronic configuration. I am writing 6. Suppose you consider a weak field ligand. Yes, splitting of d orbitals is less. Splitting is what less. Splitting of d orbitals is less. One is EZ, the other one is what T2Z. EZ and T2Z consider. After the splitting, what I am saying, consider this as what weak field. I am replacing with WF. Weak field, you imagine, you consider as a weak field. Then, once weak field ligand is there, the splitting of d orbitals is less. Once splitting is less, the electrons can fill the lower energy levels. There is no much energy difference, no. Therefore, electron can also enter into higher energy level. It is entering into the lower energy level. Similar way, it also entering into higher energy level. Therefore, pairing of electrons is not taking place when the weak field ligand is there. 6 electrons. 1, 2, 3, 4, 5, 6. Like this, 6 electrons. What is happening here? The splitting is less. Electrons are not getting paired. The electrons are uniformly filling all the orbitals, lower and higher. Therefore, you see here unpaired electrons are there. Therefore, the resulting complex is what paramagnetic. Now, you consider a strong field ligand. Consider a strong field ligand. Then splitting of d orbitals is very high. Strong field ligand is there. Splitting of d orbitals is very high. Then the energy difference between lower energy level and higher energy level is very high. You are clearly observing EZ orbitals and T to the orbitals. This is the energy difference is much in compared to this one. Once energy difference is more, the electrons cannot enter into higher energy level. The electrons have to enter into lower energy level. Once all the 6 electrons are entering into lower energy level, the electrons are getting paid in the lower energy level. Once electrons are getting paid in the lower energy levels, resulting complex is what diamagnetic. See, 6 electrons I am writing in the lower energy level only like this. Lower energy level. Once all the 6 electrons are getting paid in the lower energy level, yes, you are looking on the board clearly the diagram to unpaid electron. Once there is no unpaid electron, that particular complex is what diamagnetic. What you can understand? Simple conclusion: weak field ligands are causing less splitting. Their electrons are not getting paid, giving rise to what? Paramagnetic complex. Whenever the strong field ligand is there, splitting of orbitals is very high. Electrons cannot enter the higher energy level. Electrons are entering into lower energy levels, giving rise to what? A diamagnetic complex. So, based on the nature of the ligand, whether it is weak field or strong field, one should know the nature of the ligand. According to crystal field theory, you can easily say that whether it is resulting a paramagnetic complex or a diamagnetic complex. So, these are the important postulates of crystal field theory. Next, we see splitting of d orbitals based on crystal field theory. How the d orbital splitting under octahedral geometry, tetrahedral geometry, and square planar geometry. Let us discuss thoroughly about the splitting of d orbitals. Now, let us discuss. We have completed the postulates of crystal field theory. Now, let us see under the influence of a particular ligand how the d orbitals are splitting into different energy levels. The splitting under the influence of ligands in a octahedral geometry, in a tetrahedral geometry, in a scale planar geometry, the splitting is taking place. How this particular splitting is taking place? Let me show splitting of d orbitals in octahedral geometry. Splitting of d orbitals. Splitting of d orbitals in octahedral geometry. Octahedral geometry. Octahedral geometry. Now, let me give a diagram. Then, based on diagram, we can easily understand. We can easily explain the splitting of d orbitals. Now, I am putting a complex here. M. Octahedral geometry I am writing. Octahedral. Then writing the orbitals here. Consider this is the x-axis, y-axis, then z-axis, x, y, z. The orbitals I am writing on the each axis. Orbitals. It is now representing octahedral geometry. Octahedral geometry. Now, in octahedral geometry, the possible hybridization is d2sp3 you take, or you take sp3d2. In octahedral geometry, the possible hybridization is d2sp3 or sp3d2. Whatever it may be, either it is inner orbital complex or outer orbital complex, two d orbitals are participating in bonding or hybridization. This particular two d orbitals are easy set of orbitals. Remember, easy set. Easy set of orbitals means, you know, it is d square minus y square and dz square. D square minus y square and dz square. These two d orbitals are participating. Where this particular two d orbitals are oriented, you know well, these two d orbitals are oriented along x axis, y axis and z axis. This stands for d square minus y square orbital. This stands for what? Dz square orbital. This is what? D square minus y square orbital. This is dz square orbital. The two d orbital d square minus y square and dz square. Next, when a metal ion, consider a metal ion, you are putting into this particular metal ion is there. This metal ion you are putting into ligand solution. A metal ion you are putting into ligand solution in the first step. when a metal ion is put into ligand solution, the metal ion is occupied by all the ligands in a spherically symmetric geometry. Spherically symmetric geometry, this particular, all the ligands are approaching this particular metal ion in a spherically symmetric geometry. By this, what you can understand, all the 5d orbitals experiencing same repulsion. So I am writing like this, you see, 5d orbitals under the influence of this particular ligands from all the corners, from all the axes, these particular ligands are actually approaching this particular metal ion like this in a spherically symmetric geometry. By this, all the 5d orbitals experience the same repulsion. Their energy is what? Increase. The 5d orbitals under the influence of ligands, just they are increasing their energy. But remember, in the first step, their energy is increased, but they are not splitting. The degeneracy is not lifted. Degeneracy is not lifted, means still they are remaining unsplit. Still they are remaining unsplit means what? Remaining degenerate. Just they are increasing their energy, but remaining together, they are not actually splitting. In the second step, this is the first step of explanation. Now, in the second step, the ligands are approaching toward the metal ion along x-axis, y-axis and z-axis in octal geometry, means the ligands are approaching toward the metal ion in octal geometry. So, along x, y and z-axis, the ligands are approaching. The orbitals which are oriented along x, y and z-axis, what are the orbitals? See, easy set of orbital. This is what? Dx square minus y square orbital. This is dz square orbital. Ligands are approaching the same along x, y and z-axis. The orbitals which are oriented along x, y and z-axis, experiencing greater repulsion, their energy is increased. So, what you can write now, each set of orbitals are increasing their energy. This is what to say, xy, xz, yz, xz, this is dx square minus y square and this is what? Dz square. These are the 5d orbitals. Each set of orbitals are experiencing greater repulsion, therefore their energy is what? Increased. Increase will be for this particular easy set of orbitals. Easy set of orbitals are increasing their energy, and this particular T to the set of orbitals are oriented in between the axes. Easy set of T to the set of orbitals are oriented in between the axes. Therefore, these are actually away from the ligands. Therefore, T to the set of orbitals are experiencing less repulsion. Their energy is what? Decreased. So, once one set of the orbitals increasing their energy, the next set has to decrease. Therefore, there will be decrease in energy like this. The T to the set of orbitals are decreasing their energy. Now, the energy difference between these two sets of orbitals we are representing by, it is what either would say delta O or you say 10 dq. What I said, increase in energy, I said how much increase? Increase will be plus 0.6 delta O or you can say plus 6 dq. Plus 0.6 delta O or plus 6 dq. Here decrease, I said decrease will be minus 0.4 delta O, minus 0.4 delta O, or you can take minus 4 dq. Minus 0.4 delta O or minus 4 dq, and total energy difference between lower energy level and higher energy level is dependent by delta O or 10 dq. This particular energy difference, what we can call the d orbital splitting energy for octahedral geometry. This particular orbital, where you consider this particular easy set of orbitals, first orbital is what? Dx square minus y square, this will be dz square, and this you know well is again dxz, dyz and dxz, dyz, dxy. Let me dxy, dxz, yz, these are the lower energy level, This is what higher energy level, this is the splitting. Once again listen to me. The possible hybridization in octal geometry is D2sp3 or sp3d2. The two d orbitals involving in hybridization is the set of orbitals, that is d square minus y square and dz square. Whenever a metal ion is putting into ligand solution, all the ligands are approaching toward the metal ion in a spherically symmetric geometry. By this, all the 5 d orbitals increasing their energy. First lower in energy, increasing their energy. But degeneracy is not lifted. They are remaining in the degenerate level. They are not splitting. In the second step, ligands are approaching toward the metal ion in octahedral geometry, means along x, y and z axis. They are approaching toward the metal ion. The orbitals which are oriented along x, y and z axis, are easy set of orbital. They are experiencing more repulsion. Their energy is what? Increased. Increase will be plus 0.6 delta O or plus 6 dq. This is what increase in energy. Next, T2 set of orbitals are oriented in between the axis. They are away from the ligand. The repulsion on T2 set of orbitals is less. Therefore, their energy is what? Decreased. Decrease will be minus 0.4 delta O or minus 4 dq. Next, the total energy difference between lower energy level T2z, higher energy level EZ, represented by delta O or 10 dq. This is known as what? D orbital splitting energy for octahedral geometry. D orbital splitting energy for octahedral geometry. This way we can explain how the d orbitals are splitting in octahedral geometry.